Right, so we are doing the AC generator, as part of the electromagnetic effects chapter from unit 4. Right, so we talked about electromagnetic induction the last time and also Fleming's right-hand rule. So now we're going to move on and talk about the AC generator.
Yeah.
Alaikum assalam. So, right, the text is a bit confusing. So, right, what I'm going to do is share a video with you guys. Okay, so
Okay.
yeah, so let me just put that up. Okay, that's there, and let me share screen with you guys. All right, can you see that? Now I've put the playback speed on 1.5 just to move it along a bit quicker because it is 8 minutes long. So
Okay.
yeah, let's go through this.
Hi and welcome back to my YouTube channel. In this video, we will talk about the AC generator. AC generator is an electric machine that converts mechanical energy to electrical energy in the form of an alternating electromotive force or alternating current. AC generator works on the principle of electromagnetic induction. So when we have relative motion between a coil and a magnetic field, an electric current or electromotive force is induced in the coil. Let's look at the basic components of AC generator. Armature is part of an AC generator, which carries a current and consists of many coils of wire. Armature converts electrical power to mechanical power in the form of torque and transfers it via the shaft. Shaft is movement part and it's connected to armature. Field magnet consists of two poles, north and south pole. Field magnets are concave and cylindrical shape and therefore produce radial magnetic field. Direction of the magnetic field is from north to south pole. Slip rings S1 and S2 are connected to the armature and rotate together with it. The slip ring consists of a circular conducting material that is connected to the armature rotor windings. Slip rings are used to bridge, transfer, and carry the power to and from the rotor of an AC generator. Brushes B1 and B2 are usually made of carbon. One end of each brush is in contact with rotating slip ring, and the other end is connected to the other circuit. Galvanometer is connected to outer circuit. Purpose of galvanometer is to show the flow of current in the external circuit. Furthermore, we will explain the working principle of the AC generator. When the armature rotates between the poles of magnetic field, armature cuts the lines of magnetic field and generates current in the coil of armature. This induced current then flows through the circuits connected to the armature. In fact, it flows through the armature, slip rings, brushes, and through galvanometer, in which we have a response. As you can see, galvanometer needle swings between negative and positive values. This means that alternating current passes through galvanometer. When current is induced in the armature, it's necessary to know the direction of that induced current. So initially, armature coil ABCD is in a vertical position. Armature part AB is up while part CD is down, as you already know direction of the magnetic field is from north to south pole. Undergo half rotation in clockwise direction, part of armature AB goes down while part CD goes up. According to Fleming's right-hand rule, the thumb indicates the direction of movement of the armature part CD. It is in fact direction of the force, which is upwards. First finger points direction of magnetic field from north to south pole, and second finger shows direction of induced current. In our case, current will flow in direction DCBA of armature and from brush B1 to brush B2 through galvanometer. If we take another half rotation, part of armature AB moves up while part CD moves down. Again, according to Fleming's right-hand rule, the thumb indicates the direction of movement of the armature part CD. It is in fact direction of the force, which is downwards. First finger points direction of magnetic field from north to south pole, and the second finger shows direction of induced current. In our case, current will flow in direction ABCD of armature and from brush B2 to brush B1 through galvanometer. To conclude, induced current changes direction for every half rotation. Next thing we need to see is how induced EMF changes over time. To see this graphically representation of induced EMF, we have to assume that armature needs t seconds to complete full rotation. In time, t equals 0 seconds armature, ABCD is in a vertical position. Part of armature AB is up and part CD is down. Part of armature AB and part CD moves parallel to the magnetic field at that moment. Also at that moment, the rate of change of magnetic flux is 0, therefore induced EMF is 0. For the first quarter rotation, from t equals 0 seconds to t over 4 seconds, part of armature AB moves down and part CD moves up. In this period, induced EMF increases from 0 to maximum value. In t over 4 seconds, armature is in horizontal position in relation to the magnetic field. In t over 4 seconds, rate of change of magnetic flux momentarily gain maximum value. Therefore, the induced EMF at this position is maximum. During second quarter of rotation, from t over 4 seconds to t over 2 seconds, part of armature AB moves again down and part CD moves up. In this period, induced EMF decreases from its maximum value to 0. In t over 2 seconds, armature again is in vertical position. Part of armature AB is down and part CD is up. Part of armature AB and part CD moves parallel to the magnetic field at that moment. Also at that moment, the rate of change of magnetic flux is 0. Therefore, induced EMF is 0. During the third quarter of rotation, from t over 2 seconds to 3t over 4 seconds, part of armature AB goes up and part CD moves down. In this period, induced EMF increases from 0 to maximum value, but in this period, induced EMF has opposite polarity. In 3t over 4 seconds, rate of change of magnetic flux momentarily gain maximum value, but compared to a position in t over 4 seconds, induced EMF gain its negative value. Finally, during the last quarter of rotation, from 3t over 4 seconds to t seconds, part of armature AB goes up, part CD moves down. In this period, induced EMF decreases from its maximum negative value to 0. In time, t seconds armature is in a vertical position. Again, armature is moving parallel with magnetic field. Rate of change of magnetic flux is 0, therefore induced EMF is 0. From this graphical representation, we saw how induced current changes in time. As you probably already know, the term AC, or alternating current, generally refers to a time-varying waveform or sinusoid, and we saw that sinusoid in this graphical representation. I hope that through this video you gained new knowledge.
How much of that made sense?
Pretty much.
It did?
Yeah.
Oh, that's nice. Right, so all of that is mentioned over here as well. You've got the A, B, C, and D, right? The slip rings, the shaft, the rotation, right? They show the same. The EMF goes up, then back to 0, and then goes the other way, and that shows the position, right? So the coil is vertical with A on top and D at the bottom, right? Then it becomes horizontal, then it flips, and right, so in this full rotation it's showing what it's corresponding to, the positions, and it makes a full rotation, comes back to 0. Okay, and so that's how they're telling that the EMF first has a positive maximum and goes to 0, and then has a negative maximum, which means it's basically flowing in the opposite direction, and then comes back to 0, and that's how the alternating current goes. Right, so an alternating EMF is generated which acts first in one direction and then the other. It causes an AC current to flow in the connected brushes. The frequency of the AC is the number of complete cycles it makes in each second and is measured in hertz. 1 cycle per second is 1 hertz. If the coil rotates twice per second, it has a frequency of 2 hertz. The mains supply is an AC, an alternating current of frequency 50 hertz. Right, so that's 50 cycles per second. Okay.
Yes.
Now, practical generators. What's actually happening in generators that are used to, produce electricity? So in power stations, several coils are wound in evenly spaced slots in a soft iron cylinder. This guy. Okay. And electromagnets usually replace permanent magnets instead of having that north-south permanent magnet, horseshoe, or 2-bar magnets, whatever it is. They're using electromagnets. So the electromagnets rotate instead of the coil rotating, right? So in this case, the coil was rotating between the magnets. What they're having now is that they're having the electromagnet rotate around the coil. And we've already learned that the movement needs to be relative. So it doesn't really matter which one's moving and which one isn't, right? So it depends on relative motion, as we learned earlier. As long as one is moving in relation to the other, you're going to have electricity being generated. So it's interesting because they're using electricity to make an electromagnet out of the iron that is rotating around the core, around the coils. The large EMF and currents, which can go up to 25 kilowatt at several thousand amperes, right, induced in the stator are led through the stationary cables. Otherwise, they would quickly destroy the slip rings. So they're siphoned away. The electricity that's being generated is siphoned away. Instead, the relatively small power required by the rotor is fed via the slip rings from a small generator, which is driven by the same turbine. Right, so they've illustrated that on the next page. Right, you've got the turbine, right, the boiler steam turbine, right, the turbine is causing motion, right, of the exciter, and that is feeding into the slip rings, which is causing motion of the rotor, which is, right, generating electricity, and then the electricity is being taken away, right, and that is about the simple AC generator. Okay,
Yes.
now we have magnetic effect of a current, right? So moving a conductor through a magnetic field or moving a magnetic field around a conductor is going to generate electricity. Electricity itself also has a magnetic effect, right? And so we obviously know that from electromagnets, but that is magnetizing a metal, right? A simple wire that is carrying electricity also has a magnetic field around it, right? So that's why electricity and magnetism sort of go hand in hand. So what they're going to talk about is when you have a wire or any conductor that has electricity passing through it, it's also going to have a magnetic field around it, and you can, detect that by placing a compass near the wire, and you will see the compass deflect. And so it's only going to deflect because there is a magnetic field, and so it's going to point a certain way depending on the direction of the current. So this is a discovery made in 1819 by Hans Ørsted, and the discovery, right, like many others, was made accidentally, that the magnetic effect of an electric, like the electric current has a magnetic effect. So what you can do is you can hold a wire over, by holding a wire over and parallel to a compass needle that is pointing north to south. The needle moves when the current is switched on. Reversing the current causes the needle to move in the opposite direction, right? So depending on the direction of movement, the magnetic field, the magnetic effect of the current changes, and so that is shown by the deflection of the compass needle. Evidently, around a wire carrying a current, there is a magnetic field. As with the field due to a permanent magnet, so permanent magnets obviously have a magnetic field around them. We've talked about that, right? We represent, so a wire carrying current also has a magnetic field, and just like we did with the permanent magnets, we represent the magnetic field with field lines or lines of force, and they are drawn, right? The arrows on the line show the direction of the field and the direction in which a north, so obviously it goes north to south. Right, now how do you figure out north and south? So there's obviously a method to figure out the direction of the magnetic field, given that you know the direction of the movement of current. Right, different field patterns are given by differently shaped conductors, but in principle the theory is the same. So what this is called is the right hand screw rule. Okay, if a right-handed screw moves forward in the direction of the current, right, the direction of rotation of the screw gives the direction of magnetic field. So basically what they're saying, right, to illustrate over here, this is a screw, right, and this is a plane of paper, let's say, and the thick black line you can see is the current, the direction of the current. So it's moving from top to bottom through the paper. And the compass needle is, right, shows the direction of the North Pole. So you can see that when the current is passing through, right, you have a clockwise motion. So what you can do in this case, right, if I just, I mean, the illustration is there. How can I, yeah. So is it working? Yeah. So what you're going to do is, as you can see in the illustration, you're going to curl up your four fingers, right? And
Yeah.
have your thumb sticking out, sort of like a thumbs up, right?
Yeah.
And
Sideways thumbs up.
well, it depends, right? So what you're going to do, as you can see, is you're going to, your thumb is going to point in the direction of the current. So in this case, as you can see, the current is pointing down, right? So in this case, it's going to look like a thumbs down. And so,
Yeah.
right, if your thumb is pointing in the direction of the flow of current, then the curve, right, of your fingers of your right hand are going to show the direction of the magnetic field, the magnetic field line. So as you can see on the in the book as well, right, they're moving in a clockwise direction. So if I just look, right, that's how they're curving. They're moving in a clockwise direction, right?
Yeah. Yeah.
So similarly, right, if you take a look at this particular coil, this is a circular coil, and so, right, this part over here at the top, current is flowing this way, and so you can see that the magnetic field lines are going round the current,
Yeah.
okay, represented by these lines over here. At this point,
How do you know in which direction is the current moving?
well, obviously you'll have some information, right?
So they will be given in the question, right?
They'll either give you the direction of the current, or they might give you the direction of the magnetic field, and they'll ask you to figure out the direction of the current.
No. So in this image, how did you know that it was
The
this way?
arrow,
Like,
right, the
yeah.
circular coil, so coil, right, and they've also labeled it, the arrow is the current direction.
Yeah. Okay.
So I
So
know
it's like on the left side.
on the left side. What do you mean left side?
Like, could you show it again through your hands?
For this one,
Yeah.
right? So at this point over here at the top with this curved wire,
Yeah.
right, this is the direction of the movement of the current.
So you mean starting from here,
From where?
the thumb, right?
The thumb tells me which direction the current is moving in the coil.
Okay.
So where I'm pointing at on in the book. Okay, can you see where I'm pointing at in the book?
Yeah. Yeah. Yeah.
At this point, the arrow tells me the direction of the current. So this is the direction of the current, right?
Oh. Okay. Yeah.
Right? And so the way my fingers are curving are showing the direction of the magnetic field. Right? So they're going like this. Circular.
Yeah.
Like they will be in the same direction.
Well, it depends on, right? I mean, they're going to sort of curve round. The very center one is going to be straight round because the wire is not, straight. It is curving. And so, as you can see over here, right, the magnetic field is sort of bending. So, right, they're going to go this way, and then it's a bit difficult to, right? So, at the points where the wire is coming through the plane, you can say that it's sort of coming out at this point, right?
Yeah.
And so if I right? If that's the direction of current, then this is how my fingers, right? And that is also what the paper is showing. The other end over here, the current's going in, and so this is how the current, the magnetic field line, sorry, right? This is
The
how
current.
the no, not the current. The current is the thumb. So the
Yeah.
current is going down.
Yeah. Okay.
And so
Okay.
the magnetic field line that is being produced by the current is going this way,
Oh. Okay. Okay. I got it.
right?
Yeah.
Does that make sense?
Yes.
Okay. Oops. So that was a field due to a straight wire, which is pretty simple. A field due to a circular coil that we just talked about. And then there's a field due to a solenoid. So what is a solenoid? It is a long cylindrical coil. And let me just go back. So it is a long cylindrical coil. It produces a field similar to that of a bar magnet. And right in the figure, end A behaves like the North Pole and end B behaves like the South Pole. Right, so we just take a look at that. Oh, sorry, here. Right, this is behaving like the North Pole and this is behaving like the South Pole. And so you can see
Yeah.
you can see that if you sort of point with the direction, so you can see that the magnetic field lines are sort of right very varied depending on uh, because the coil is going round and round over this piece of like iron, the coil. So if I just take the general direction, this is the direction of the coil, like so and the current. And so the magnetic field lines, as you can see, that they're going and they're curving around the coil, right?
Yeah.
It's better illustrated with these two over here. These ones
Yeah.
are going to be the same, but they're going to go like all the way
Upwards.
out. Yeah, no, they're going to go make a bigger sort of circular path, a longer
Yeah.
circular path, right? Now, when the current goes the other way, right? So over here it's coming up at the back side of the coil, it's going down,
Yeah.
right? So
Yeah.
when the wire's curving back, the current is obviously going down, and so the magnetic field is going to be,
Round.
and you can see that over here with these two field lines clearly. And then this one, which sort of doesn't like it's going to obviously make a circular path, like an oval path as well, but it's going to be longer, so it's going to go out the edge
Like
of
the longest one of all.
like it's not about longest road, but it's going to be more spread out.
Yeah.
Okay, so that is how you can figure out the so this is the right hand screw rule or the right hand grip rule, right, whatever you want to call it. Does it make sense how to use it? So there are a number of rules. Okay, we've come across the Fleming's right hand rule, and now you've got the right hand screw rule or the right right hand grip rule. Okay.
Yes. Okay.
Okay. Now, in fact, right, for a solenoid, it's sort of different. Let me go over that again. So the screw rule for a straight wire or a field due to a circular coil is, right, the thumb is showing the direction of the current and the fingers are the direction of the magnetic field. The right hand, right, you can use it, which I did. Okay, Alternatively, the right hand grip rule, so this is slightly different. Now, again, right, we need to know both, but it can get a bit confusing. What they're saying is that using your fingers, you curve your fingers in the direction of the way the coil of the conducting wire is being curved around the solenoid. So, right, they're going from top to bottom over here. So if I take my fingers and I curve them this way,
Yeah.
like the coils of the wire,
Like a
then
claw.
yeah, sort of. And so what that's going to do is the thumb is going to tell me where the North Pole is,
Oh, okay.
right? It can go, I mean, either the right hand screw rule, in which the thumb is telling me the direction of the current and my fingers are telling me the direction of the magnetic field lines. This can also tell me where the North Pole is. Why? Because the field lines, if this is the direction of the current, as you can see with the arrows, right, then this is how the field line is going, right? And so that tells me that the direction where the field line is starting, right, that is the North Pole, and it is going towards the South Pole. But this, in some cases, in solenoid, because it is circular, it can be confusing. You can confuse the North and South poles. And so using the grip rule, where you're using your fingers instead to show the direction of the coil, right, the way the coil is turned, and you stick your thumb out, right, and so the direction
Yeah.
of the thumb is going to tell you where the North Pole is. And if you know where the North Pole is, right, you know
Yeah.
that the magnetic field lines are going to move from the, so if the North Pole is in this direction towards the left, then obviously towards the right you have the which pole?
South.
South
South.
pole, right? And then you know that the magnetic field lines are going to go from north to south,
Yeah. Yeah.
right? And we know in a magnet the field lines go both ways. So from the top, which is what's facing you, it's going to go from north to south like this. And from the back over here, it's going to go north to south like this.
Okay, that actually makes much more sense. Yeah.
So if you find that easier to deal with, it's just that the naming, right? So over here, the screw rule is the thumb pointing in the direction of the current and the finger showing the direction of the magnetic field lines. That is the screw rule, the right hand screw rule, right? And that is used
Fine.
for current passing through a wire and then figuring out the direction of the magnetic field. The right hand grip rule is used for solenoid. So only if they give you a situation where there's a solenoid and they're asking you, oh, figure out, where the North Pole is. And so you curve your fingers as the coil is curving in that same direction. You stick your thumb out, right? And you get the North Pole. Or in case they're telling you, right, that, the North Pole is this way. And so you just curve your fingers and like, oh, the North Pole is this way. And so how is the coil turning? And so it's turning like this, because North Pole is, sort of like diagonally upwards.
Yeah. Okay.
The confusing part that confuses students over here is just like there's right. We're not done. We're going to come across Fleming's left hand rule, and I believe another one as well. Right, and so all those different rules where you're using your either right hand or left hand and going like this or this or this, that sort of ends up confusing students. If you can keep track
Yeah.
of that, well and good. Okay.
Okay.
All right. So going back to the book, variation of magnetic field strength. So there is a variation of magnetic field strength around a current carrying straight wire. It becomes less as the distance from the wire increases, which makes sense, just like the magnetic field strength becomes less as you move further away from the magnet, right? This is shown
Yeah.
by the magnetic field lines becoming further apart, right? So you can see over here, right? The magnetic field lines become further and further apart. So the further you go, the lesser the magnetic effect. When the current through the wire is increased, the strength of the magnetic field will also increase. So more current means stronger magnetic effect. And when there's a stronger magnetic effect, the field lines become closer together. When the direction of the current changes, the magnetic field acts in the opposite direction. Also makes sense because we are determining the direction of the magnetic field based on the direction of the flow of current. If the current is flowing in the opposite direction, the magnetic field will also change.
Yes. Okay.
You following?
Yes.
No issues?
No.
Okay. Haram, are you following? You're rather silent today.
Well, if she isn't asking questions, that means she might have understood.
Hopefully.
Yeah.
Inside the solenoid, the field lines are closer together than they are outside the solenoid. Right, so inside over here, that's the part inside the coils. You can see that the field lines are closer together. Outside, they're further apart. Why? Because there's so many turns of the coil that there's more current, and so there's more magnetic field inside, right, than the effect of the current on the outside. Right, this indicates that the magnetic field is stronger inside the solenoid than outside it. When the direction of the current changes in the solenoid, the magnetic field acts in the opposite direction. The field inside a solenoid can be made very strong if it has a large number of turns or a large current. So either or both. Right? Permanent magnets can be made by allowing molten ferromagnetic metal to solidify in such fields. Okay. So a key definition we have: variation of magnetic field strength is the magnetic field strength decreases with distance from a current carrying wire and varies around a solenoid. Okay.
Yes.
Okay. Now applications of magnetic effects of a current. So one thing is a relay, and so there are a number of these. So let's quickly go
Can we
over
take a 10-minute break?
after we talk about this.
Not before that.
Not before that, because after the break we'll move on to a new topic, which is force on a current carrying conductor.
Okay. Is this a large
It's
topic?
it, it's just how stuff works.
So reading stuff?
Well, yes.
Okay.
Right. The reason I've been using the book and not the whiteboard for this is because of all the illustrations. Right. So the concept and the illustration in the book, I felt if I just show it to you, it would be better to explain. Easier to explain. So
This topic is not included in the O level syllabus, no? Or is it?
right. So let's move to electromagnetic effects. And the Fleming's right hand rule is not in O level. Practical generators is not in O level. Magnetic effects of a current,
Though, is it in IGCSE, right?
it is. All of this is in IGCSE.
Okay.
Thank God.
Thank God.
Well, I mean, all of what we just discussed, the right hand screw rule and the right hand thumb rule, is part of the O level syllabus. Variation of a magnetic field strength is part of the O level syllabus. And applications
It's easy.
that's easy. That's nice.
Yeah.
Yeah. So
It's easy.
I mean, if
Wow.
she finds it easy, that's nice, right? Remember that the working of the simple AC generator is part of your O level syllabus. The practical generator
Yeah.
is not.
Okay.
Yeah, so this thing is what, like, you need to know how this thing works, right? And then
Okay.
applications, right? You have fewer applications. Like the electric bell is not part of the syllabus. It's only the relay and the loudspeaker. Whereas for the IGCSE, we have the relay and the reed switch, which isn't even mentioned in the O level book. And then you've got the loudspeaker and the electric bell. So you've got all of it.
Okay.
Right. So coming back over here, how stuff works. A relay. So a relay is something we came across earlier as well in practical applications of electricity, electric circuits. And right, it's a switch based on the principle of an electromagnet. It is useful if we want one circuit to control another, especially if the current and power are larger in the second circuit. Right, so the illustration on the next page, we'll take a look at that, shows a typical relay. When a current is in the coil from the circuit connected to AB, let's take a look at that. So this is circuit AB and this is the coil, so this is an electromagnet. So when a current is in the coil, the soft iron core is magnetized and attracts the L-shaped iron armature. So this guy over here, right, the iron armature, it's attracted. What this does is it sort of causes
Okay.
something.
No, your voice just went off for a minute.
Yeah, the yeah, so the USB connection for my mic, I've put it on a USB hub and it's rather flimsy, so it does that sometimes. Okay, so as I was saying, that the iron armature over here is going to be attracted towards the solenoid, right, the electromagnet, and that's going to cause the horizontal part to push up. When it pushes up, this part, see, you can see there's a small gap. If it just zooms in, yes, you can see there's a gap. That means this circuit connection DE is not complete. So when it pushes it up, it causes the connection to complete. They touch, and so current can flow through. So coming back over here, right? This rocks on its pivot and closes the contact C in the circuit connected to DE. The relay is then energized or on. Okay. So what happens then is that the current needed to operate, right? So this is how it works. So one circuit controlling another circuit. The current needed to operate a relay is called the pull-on current or drop-off current. It is smaller, right? Sorry, and the drop-off current is the smaller current in the coil when the relay just stops working. So the current needed to operate the relay is called the pull-on current, and when the relay stops working, it's the smaller current and it's called the drop-off current. If the coil resistance R, so this guy over here, for a relay is 185 ohms and it is operating with the potential difference of 12 volts, then we can figure out what the current is. So 12 divided by 185 is giving you 0.065 amperes or 65 milliamps. And these are the symbols for a relay, right? So the symbols for relay, which normally open, normally closed contacts, are given over here. So this is an open relay and this is a closed relay switch. All right. So yeah, how stuff works. Obviously, some concepts are being applied which you come up, which we've just covered recently and last time as well. Are you following?
Okay.
Is it okay so far?
Yes.
Yes.
Okay. Next is something called the read switch. Now, obviously, Haram, you're in O level. This isn't even given in the book. So you can sort of like you can pay attention just for this, benefit of knowing how this works.
Or you can slack off.
That too. You, on the other hand, cannot,
Wow.
right?
Okay.
One such switch, like a read switch, right, is shown over here. So you've got this glass tube, right? And there are reads A and B, these pinkish lines, and then there's a coil of wire around it. So when current flows in the coil, the magnetic field produced magnetizes the strips called reeds of the magnetic material. Right, so this A and B is magnetic material. It becomes magnetized when current flows through the coil. The ends become opposite poles, sure, right? And so if we use the right hand grip rule, we can figure out which end is going to be the positive and which end is going to be the, sorry, not positive, the north pole and the south pole, right? So you curve your fingers in the direction of the current in the coil, and the direction your thumb is pointing to will be the north pole. So the ends become opposite poles and one reed is attracted to the other, so completing the circuit AB. So these guys join up. The reeds separate when the current in the coil is switched off. This type of reed switch is also sometimes called the reed relay. Okay, simple enough. How are they used? Reed switches are also operated by permanent magnets. This figure shows over here. So there's a permanent magnet over here. There's a permanent magnet over here, right? And it shows the use of a normally open reed switch as a burglar alarm. When the door is closed, the magnetic fields of the magnet in the door and the door frame cancel each other out. Okay, you can see the orientation. On the door, it's north pole upwards. On the frame, it's south pole upwards. So they'll attract each other, right? And when they're closed, they'll cancel each other out. And the reed switch is open. When the door is opened, the magnetic field of the magnet in the door frame closes the reed switch. Right over here, sorry. This is the switch. You can barely make it out in the illustration. Just zoom in over here. Right, so when it's closed, yeah, so this guy, when the door opens, the magnetic field of this magnet has an effect on the switch which closes it. Right, and so current will flow through this thing and the alarm will so that current flows in the alarm circuit if it has been switched on. Right, now first thing, the alarm needs to be switched on. So there's a double switch over here, right? I switch it on, right, when I'm closing the shop or when I'm going to bed or whatever, right? And I close the door and I leave. So nothing's going to happen when the door is closed, provided this switch is closed. So the circuit is complete from here, right? If there's a burglar, they'll open the door, right? They'll break the lock, they'll open the door. As soon as they open the door, the magnetic field of the magnet on the frame is going to cause this switch to close. The circuit will become complete and the bell will go off.
Okay.
So there are like two switches. One is the switch that you control manually, and the other is the reed switch that is controlled by a magnetic field. Okay. Loudspeaker,
Yeah.
right? Just bear with me. We're almost done with this part, then you guys get a break. So how does a loudspeaker work? Varying currents from a radio, CD player, or stuff like that pass through a short cylindrical coil whose turns are at right angles to the magnetic field of a magnet with a central pole and a surrounding ring pole. So this is the magnet. It has a central pole, which is the south pole, a surrounding ring that is all north pole. Right? This is the paper cone over here. Right? and you obviously have current passing through. So the magnetic field around the coil and the magnet interact, and the coil vibrates with the same frequency as the AC of the electrical signal it receives.
Okay.
A paper cone attached to the coil. So over here you can see, right, North Pole on the outside, South Pole on the inside, and the explanation they're giving, the cone attached moves to the coil, moves with it and sets up a sound wave in the surrounding air. So yeah, that happens with the loudspeaker. Again, just like stuff you need to know that, oh, this happens. And finally, the electric bell. I'll just position it this way so that the text and the illustration are clear. So you can see the circuit, right? There's the bell push. So when you push the bell, you complete the circuit. Current flows through, right? So how does that work? When the circuit in this figure is completed, when you pushing the bell, right? Current flows in the coil of the electromagnet over here. So you can see the arrow telling the direction of the current. It goes in the electromagnet, so all the coil and everything, right? And you can see that on the two arms of the electromagnet, the coil is wound in opposite directions, so current is flowing in opposite directions. So you're going to have one north pole and one south pole over here, right? So if we use the right hand grip rule over here, the north pole is pointing towards the left, and so this guy is the south pole, and for the arm on top, this is the north pole on the outside, right? So south pole and north pole over here, right? You can try that yourself as well.
Yeah. Okay.
And right, it becomes the right current flows through the coil, and this guy becomes magnetized and attracts the soft iron bar. So this thing, right, this soft iron armature is pulled towards the magnet, and as is pulled towards the magnet, right, it strikes the gong, and that makes the noise. So the hammer hits the gong, but the circuit is now broken, right? Because the circuit, right, the current is actually passing over here to the metal strip, and then to the screw, and then back. So when the iron arm, like the iron bar, is attracted to the magnet, there's a gap between the iron bar and the metal strip, right? And so the contact is broken, and so this becomes demagnetized, and so the iron bar moves back. And so that happens rapidly. You get like ding, 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 and so that's the iron bar moving back and forth, right? The contact is made, it moves towards the magnet. The contact is broken, it moves back. The contact is made again, it moves towards. And so as long as, right, the bell is pushed, right, that's going to keep happening. So the electromagnet loses its the hammer hits the gong, but the circuit is now broken at the point C of the contact screw over here.
Yeah. Okay.
The electromagnet loses its magnetism and no longer attracts the armature. The springy metal strip is then able to pull the armature back. So this thing moves ahead. Contact breaks over here, right? It hits the gong. It moves back, right? Touches the contact again. Current flows again. It becomes magnetized, comes back, right? And so the springy metal strip is then able to pull the armature back, remaking the contact at point C over here. And so completing the circuit, this cycle is repeated for as long as the bell is depressed or basically pushed, and continuous ringing occurs. Is that clear?
Yes.
Okay, so we'll stop here, and I'll see you guys in about 10 minutes, and we can talk a bit about force on a current carrying conductor.
Okay.
All right?
And
Allah Hafiz.
Yes. Allah Hafiz.